we're back, and today we're looking at bond and molecular polarity in the topic of bonding, okay? These structures should be familiar to us because we used them in the last two videos in terms of drawing the dot structures and also shapes, right? We're going to use them again in terms of bond and molecular polarity, okay? All right, so we're looking at bond and molecular polarity. Okay, all right. Some background. We've heard of the poles, right? On the Earth, North and South Pole, we've heard of poles of magnets, right? And we think of those guys as opposites, North and South, right? So we're going to use that same context and think of poles as opposite charges, okay, within a molecule, all right, or a bond, depending on which one we're talking about. Now, going back again, and remember we say over and over and over again, chemistry is foundational. We have to know how to draw dot structures, okay? We have to know to interpret the shapes, alrighty? And those two guys combined will help us figure out in terms of whether a bond is polar or whether a molecule is polar, especially within the molecule, okay? So please review those guys, okay? Drawing the shapes, the covalent compounds, and drawing the proper dot structures. All right. So once again, guys, it all goes back to what? It all goes back to the valence. All right. Electrons. Okay. It goes back to the central atom. All right. Remember we did some of the other videos recapping. Remember the atom that forms the most bonds. That's going to be your central atom. It goes back to shared. All right. And unshared, okay, pairs, okay, and unshared pairs specifically on the central atom that helps dictate the shape also. So once again, I keep saying it, please review, please review, please review, then on the molecular polarity will make a lot more sense. Okay, so we have HCl, I'm going to redraw it again. HCl, and remember you always have your reference tables. H has 1 valence electron. Chlorine, we know, famously has 7 valence electrons, right? Okay, chlorine wants to get to an octet, all right? Hydrogen wants to get to a duet. They're non-metals only, so we're not using brackets and charge. We're going to share, okay, to get to a full valence shell. So, these two guys, they share right here, and this is called a single covalent bond. So we're just recapping, right? The shape of this guy, right, is linear, all right? We discussed that in the last video, no problem, all right? Because you can draw a line through all the atoms, okay, imaginary line. Now, in terms of polarity, right, we have to look at, let's look at bond polarity first. In terms of bond polarity, all right, you have to look at the difference, delta sign, difference in electronegativity. Very, very important, right? And very simple. Because all you need to do is just open up your reference table. The electronegativity values for the atoms are there. And as I said before, right, we agreed that our definition of electronegativity is going to be the attraction, right, that an atom has for electrons in a chemical bond. So here, right, HCl, hydrogen is trying to attract chlorine's valence electron towards himself. He's pulling this way. And chlorine is pulling this way. All right? Attracting hydrogen's electron towards himself. They're sharing, but there's still a tug of war going on, guys. All right? So here's the deal. You look at electronegativity values, and that tells you who's winning the tug of war. All right? So we know hydrogen is about 2.2. And chlorine, I forgot, I think it's 3 point something, 3.0, but let me check to make sure. Alrighty. Alright, chlorine, alright, 17, chlorine's 3.2. Yeah, I guess still got it. Okay, chlorine is 3.2, alrighty. So what's gonna happen, guys? Chlorine is gonna win the tug of war, okay? So the pull is gonna go more in this direction. The electron cloud is going to be more on chlorine's side. Because remember, electrons are negative, they have a cloud around them, charged cloud model. The cloud is going to be distorted or more on this side, and the cloud is going to be more bulkier on this side. So this side will be partially negative, something, and let's say someone's pulling the blanket more towards himself, they'll be warmer. Think of the warmth as an analogy for a negative charge. Blanket's a negative charge, or warmth, more on your side, you're warmer, you're more negative. So the funny symbol right there means partial, it's partially negative. It's not fully negative. We didn't lose the electron, hydrogen didn't lose its electron, but the electron cloud is more on that side, okay? So this bond now, guys, has what? Two poles, or a dipole, right? Di meaning two, pole, opposite charges, okay? So that's a dipole or a polar bond, okay? All right. Now, water, we know from experience, right? Oxygen has 6 valence electrons. He's the central atom because he forms two bonds. Hydrogen only forms one bond, okay? So that's why oxygen is a central atom in water. Link them up. We agreed from the last video that the unshared pairs here, they cause what? They cause repulsion, and they push these guys down, okay? Push them away. So that's why water does not have a linear shape. Water has a bent shape, okay? All right. Now let's look at polarity of the bond. Just look at these two guys right here, hydrogen and oxygen. Okay, hydrogen is 2.2, and oxygen is around 3.5, okay? Alrighty, so who's gonna win the tug of war? Oxygen, right? Because he has a higher electronegativity, a higher attraction for the electrons in the bond. So the pull is gonna go towards the oxygen, so he'll be partially negative. That's how you know, folks, all right? So bond polarity is very simple. Just look at the electronegativity differences, you're good to go. The higher electronegativity gets a negative charge. By default, the guy with the low electronegativity, he'll be partially positive. Higher electronegativity, partially negative. So the hydrogens will be partially positive and partially positive, okay? So we're going for the bond polarities, okay? All right, for NF3 over here, right? You can draw it. N has 5 valence electrons. 1, 2, 3, 4, 5. You have 3 Fs, 3 fluorines. I'll draw them out right here. They have 7 valence electrons. I'll draw them in here. Now, guys, I'm drawing them in quickly because we did this already in the other videos, right? But I'm just recapping. I like to recap. No problem. Bam. All right. You guys remember what shape is this? All right. This shape is trigonal pyramidal. Okay. This is a bend shape. This NF3 is trigonal pyramidal. All right. Pyramid. M-I-D-A-L. Okay. Bam. Done. All right. Now, most people say trigonal pyramidal. All right. No problem. Pyramidal. Depending on how you want to pronounce it. But who's going to win the tug of war, people, between the N and the F? Now, fluorine just so happens to be the most electronegative guy on the periodic table. He's 4.0, right? On your reference table, table S. Okay. And nitrogen, I got to take a peek. I'm guessing around 3.0. Okay. Nitrogen is 3.0. Yep, still got it. Bam. Okay. Alrighty. So fluorine wins the tug of war. You win the tug of war. You pull the electrons more toward yourself. All right. Partially negative. Remember, partially. He's not fully taking electrons, but they're moving more towards him. All right. So all these fluorines are partially negative. The nitrogen is partially positive. Okay. So this right here is a polar bond. Okay, because you have a negative and partially positive charge buildup. Okay. CCl4, carbon tetrachloride. Carbon has 4 valence electrons. He wants to make 4 bonds. Chlorine has 7 valence electrons. Okay. He only wants to make 1 bond. Okay, because 7 plus 1 gives him 8, stable octet. That's all he needs. All right. So we can always put your dots in, people. Okay, don't take shortcuts. once again, guys, chlorine here is going to win the tug of war. He's more electronegative, so he will be partially negative. So all around is partially negative, partially negative, partially negative, partially negative, right? So this guy has what? Has polar bonds, okay? Alrighty. So, now something like, let's say we had a draw right here. This is a simple guy. Let's say we have F and F, right? Two F's together, bam. Diatomic molecule. Anytime you're a diatomic molecule, no one is going to win the tug of war because you have the same electronegativities, right? So this bond here will be non-polar. So if you have the same electronegativities, okay, the bond will be non-polar. If you see a difference in electronegativity, the bond is polar, all right? Okay, so let's look at molecular polarity. We agreed, right? Bond polarity is simply what? It's simply difference in electronegativities, right? Let's look at molecular polarity. Now, when we look at molecular polarity, right, we have to look at something called either the charge distribution, okay, or you can check with symmetry, the symmetry of the molecule. Is it symmetrical? Is it symmetrical? SYMM for short, or is it asymmetrical? All right? All right, so how do you figure out if it's symmetrical or asymmetrical? So, look at it, let's talk about charge distribution first. Charge distribution. If one side is positive and the other side is negative, that means it doesn't have the same charge distribution all around, okay? So for charge distribution, right, if it's the same, right, make a note of this, if it's the same all around, okay, your molecule is going to be symmetrical, all right? And if it's not the same all around, okay, it's going to be asymmetrical, okay? So if you have the same charge distribution all around the molecule, symmetrical. This does not have the same charge distribution all around because we know from these partial charges, right? It's different, right? So this molecule right here, HCl, okay, is an asymmetrical molecule, all right? Now, once you know it's an asymmetrical molecule, you can follow something called a SNAP rule, S-N-A-P, S-N-A-P, for molecules, right? And it simply says, if a molecule is symmetrical, it's going to be non-polar, all right, for molecular polarity. If a molecule is asymmetrical, asymmetrical, it's going to be polar, all right, SNAP, symmetrical, non-polar, asymmetrical, polar, all right. So this is an asymmetrical molecule, therefore HCl is polar, so polar molecules, because it's asymmetrical. Water, charge distribution. One side of it is what? One side is positive, the other side is negative, okay? It doesn't have the same charge distribution all around. This is an asymmetrical molecule, okay, guys? If you're asymmetrical, okay, you are going to be a polar molecule. Polar molecule, alrighty? Done, all right. Moving on to this guy right here, okay? So what do you think? Trigonopyramidal shape. All these guys are negative. This side is positive. That's another asymmetrical molecule. Asymmetrical molecule. So you see the pattern with the charge distribution? Just look at the different size people, all right? And you're good to go. You go around the molecule, all right? Asymmetrical molecule, and it's going to be polar, all right? CCl4. We established a bond polarity, right? And each of these bonds are polar bonds, right? But let's be careful. Let's look around it. This side's negative, that side's negative, that side's negative, that side's negative, okay? What we have, right? The central atom is stuck in the middle, right? We're looking all around it, right? All around has the same charge, okay? So it has the same charge distribution all around, so you can automatically assume that this is a symmetrical molecule. And any symmetrical molecule is going to be what? Is going to be NP, non-polar. Okay, remember the SNAP rule, right? Symmetrical, non-polar, asymmetrical, polar. Okay, all right, so we did these guys right here. All right, now notice for CCl4, right? As we're winding down. The bonds are what? The bonds are polar. Write it down here, B-O-N-D. The bonds are polar. Remember, bond polarity, right? We just checked electronegativity difference, right? So CCl4 has a polar bond. Difference in electronegativity, bond is polar. But because the charge distribution all around, right, is the same, okay, it's a symmetrical molecule, the molecular polarity is non-polar. So please make that distinction. Bond polarity versus charge distribution around the molecule, that's the molecular polarity. That's going to just govern the molecular polarity. All right, just want to show you something real quick. That's charge distribution, right? You can also check reflectability, people. You can, this molecule right here, if I could imagine this is a mirror, does it reflect on both sides? No, it doesn't. So that's a asymmetrical molecule right there if it doesn't reflect. Okay? Now water right here, right? Put it like this, it reflects nicely this way. The H's fold onto each other and reflect, right? But if you put it like this, right? This side, these two H's right here, there's no two H's to match it over here, right? So there, in terms of symmetry, it's asymmetrical, right? So you can use the reflectability, I call it, and make a made-up name, all right? Or the symmetry in terms of that. Or you can use the charge distribution, all right? Pattern, okay? Either or works, right? But if they ask what charge distribution, you know what it means, no problem. Okay, let me see. Let's do two more, call it a day. So we got CO2, our friend over here, right? Carbon dioxide. So, bam, carbon goes in the middle. Forms 4 bonds, oxygen only forms 2. Now guys, when you keep doing these guys, after a while you're gonna automatically see who the central atom is, the guy who makes the most bonds, because the valence electrons and how many bonds they form will be stuck in your head. Okay? 6 dots, 6 valence electrons. 6 dots around the oxygen. 4 dots around carbon. Okay? He's gonna do what? He's gonna go bam, 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 and bam, right? So this is carbon dioxide, 2 double bonds, yes? Now, it just so happens oxygen has a higher electronegativity than carbon, right? So oxygen is going to win the tug of war in both instances, okay? The pull will be this way, the pull will be this way. So the bond for CO2 is polar. Polar bond. This bond's polar, that bond is polar. Now tell me now about the charge distribution. We agree, right? It's sort of kind of the same all around, yes or no, okay? Tell me about the reflectability. Tell me about the symmetry in terms of that. It's the same all around. This guy reflects nicely that way, okay? Reflects nicely this way, bam, bam. Also this way, right? Same thing, right? So it's a symmetrical molecule. So the molecule for CO2 is non-polar. How do I know it's non-polar? Because the molecule is what? The molecule is symmetrical. How do I know it's symmetrical? It has the same charge distribution all around. Okay? No problem? Alright. And this guy right here, let's draw this guy real quick. This one gives like students a little, nightmares. But I know carbon is a central atom. He forms 4 bonds, so I'll put my 4 dots on him. Then I'm going to work with hydrogen. I know hydrogen can never, ever be in the middle, right? So put hydrogen there, hydrogen there, hydrogen there. Things that form 1 bond, never a central atom, okay? Never a central atom. Bam. So it's like a puzzle. The guys with the straight edges always go on the outside. Alright? So I think it's like that. I never look at these structures and go, oh my gosh, I can't do it one time. Okay? I always say, you know what, it's like a puzzle, and I figure it out. Alright? So I can't put hydrogen in the middle, so I'm going to put oxygen here. Oxygen, yes? I got my 4 oxygen, my 6 valence electrons. Bam. Okay, I'll link up those guys right there. I know oxygen wants to form 2 bonds, so I know that hydrogen is going to link up with him. Bam. Okay, there we go, we're done. It's a structure, right? Now, in terms of, there's a bit of controversy, right? The C and the H bond, for our purposes, they're different electronegativities. They're polar. When you go to college, sometimes they say 0.4 to 0 is non-polar, but we're not going to worry about that. We have a difference in electronegativity here. Okay, we'll call it a polar bond. Okay? Now, in terms of, so let me say bond is polar. Alright? Okay, or between the C and the O, there's a difference in electronegativity, polar, right? But tell me about the symmetry of the molecule symmetrical, guys? Look at it carefully. When you put this right here, that's hydrogen, yes? This is O and hydrogen, right? So these guys here, they do not reflect, yes or no? So automatically, right, you can assume this molecule in terms of charge distribution and symmetry is asymmetrical. Asymmetrical. And if the molecule, right, is asymmetrical, it is a polar molecule, okay? Because it doesn't reflect perfectly all around. All right, guys, we did a lot of structures. We did bond polarity, molecular polarity. Bond polarity is difference in electronegativity. Molecular polarity, check your charge distribution, check the symmetry. Snap rule, you're good to go. As always, hard work with sacrifice equals success. Take care, guys. Study hard.